Okay, so this is section 5.3, which is the theory-based approach for comparing two proportions. So, in chapter 1 we talked about types of distributions and symmetric bell-shaped distributions for simulating differences between proportions, right? So, when all of this theory-based inference stuff is designed to make sure that we've got that nice bell-shaped distribution, that's what the validity conditions are for. So, assuming that we have that bell-shaped distribution, what we need is just the standard error of the statistic under the null hypothesis. Okay, and that's enough to do theory-based inference. As with all of the theory-based inference we've done before, the z-test for the difference between two proportions is the observed statistic minus the hypothesized value divided by the standard error of the statistic under the null hypothesis. So in this case, it is p hat 1 minus p hat 2 minus 0 divided by the standard error of p hat 1 minus p hat 2. So our null hypothesis by default is that pi 1 equals pi 2. So we're assuming that is true, which means that we can create a pooled proportion of success. So that's equivalent to the number of successes in group 1 plus the number of successes in group 2 divided by the total number of observations. Okay? Once we've got that, we have a proportion. We know how to get the standard error of a proportion. Right? So, we have p hat times 1 minus p hat over n in the normal case. The only thing we don't have a direct analog for right now is that n. So the next thing we do is get a pooled sample size. So what this does is this accounts for the fact that if you have 2 people in group 1 and 50 people in group 2, you've still got a lot of variability because of that, really small sample size in group 1. If you have equal numbers of people in group 1 and group 2, then you've got a much more similar standard error of each of the 2 group proportions. All right. So if we plug this into this one proportion formula, we get p hat times 1 minus p hat divided by this pooled sample size, which works out to be p hat times 1 minus p hat times 1 over n1 plus 1 over n2. And that is the formula for the standard error of p hat. Okay. Now remember, this only holds when we're assuming that the null hypothesis is true. And the p hat is only used for that standard error calculation. So don't get it confused with p hat 1 minus p hat 2. Okay. So if we substitute this back in, we get our z statistic to be p hat 1 minus p hat 2 divided by pooled p times 1 minus p hat times our pooled sample size. Alright, it's relatively simple. This p hat calculation looks scarier than it is. Remember, it's just the total number of successes in both groups divided by the total number of observations in both groups. Alright, so that's how you do a z-test. You take your z-value. If it's bigger than 2, then you can reject the null hypothesis. If it's not bigger than 2, then you fail to reject the null hypothesis. Otherwise, everything's pretty much the same as it was in chapters 2 and 3. Right? Okay. Now, confidence intervals that are theory-based for the difference between two proportions. In our z-test, we assumed that the null hypothesis was true and that the 2 sample proportions were the same, right? That made our standard error calculation a little bit simpler, but when we do a confidence interval, we can't make that assumption, right? Remember that confidence intervals only implicitly have a hypothesis test. So when we make a confidence interval, we're estimating the actual value, first and foremost. So we can't make that assumption, which means that our standard error formula gets a little more complicated. We have the full standard error of the first group plus the full standard error of the second group, right? We add those together and take the square root, okay? This squared value, if you ignore the square root sign, is the variance, which is a measure of the variability for each of the two populations. You add those together and take the square root to get the standard error, all right? But these both look pretty similar, and if we go back over here, the standard error formula for the z-test is pretty similar looking, right? And actually, if you plug p hat in here for p1 and p2, you can factor it out and get the exact same formula, okay? So one of these is a special case of the other. If we use the confidence interval formula, sample statistic plus or minus the multiplier times the standard error, then we have a formula for a theory-based confidence interval for the difference in two proportions. As with everything else, the multiplier in this class is always going to be 2, and that gives us an approximately 95% confidence interval. So the only thing we have left is to figure out what the validity conditions are so that we ensure that we have a nice bell-shaped symmetric distribution. And to get that, we need 10 observations in each cell of that 2x2 contingency table. Okay, so 10 successes and 10 failures in each treatment group. If you have that, you can do a theory-based test or an interval. If you don't have that, you can always use the simulation-based methods. All right, so that concludes chapter 3. Really, this whole thing is pretty similar to what we've been doing, so I hope that it's not too confusing. I would encourage you to do the practice problems in the worksheet that I will post later today, March 16th, and work through the practice problems on the practice test. But if you understood chapter 3 relatively well, hopefully this just seems like the same thing all over again. If not, please remember to post questions to the discussion board, and if you do understand what's going on, feel free to answer questions on the discussion board. I will be handing out bonus points for people who participate using the discussion board, just to encourage you to do that like I would normally have encouraged you to attend class. All right? So, hope you guys are doing well, and I think this is probably the last lecture for like a week or more. So, see you later.